let's say we have a beam line with, say, a quadrupole there. It's a quadrupole, and maybe a screen here. So that's our screen, and then we have these particles, electrons, for example, electrons traveling through the quadrupole, falling on the screen. Okay. Now, and let's say that the transfer matrix from there to the screen, the transfer matrix over this region, let's say it's M, and let's say the elements of this transfer matrix, let me call them C as C primed and S primed. So these elements would change when the quartz strength changes. So C and S would take on different values as we do the quartz scan. And as we do the quartz scan, the beam image at the screen, will have different x squared, different average x squared, or I'll use sigma squared to represent that. And let's say at the entrance of the quadrupole is where we like to find the twist parameters and the emittance. So these are epsilon, alpha, beta, and gamma. So that's what we hope to find. And we hope to find this by changing the quartz strength, which changes the matrix elements and changes the beam width. Okay, so without going through all the mathematics, I'll just write down the equation based on the theories about twist parameters and so on, that relates the sigma squared, the beam width squared at the screen, to the twist parameters. So that, okay, so here goes sigma squared of the beam at the screen, that is equal to, okay, so this is how it looks like, it's equal to C squared, C is this matrix elements, times minus of alpha epsilon, alpha times emittance, plus 2 CS times beta epsilon plus S squared times gamma epsilon. Alright, so this relates the twist parameters alpha, beta, gamma, and epsilon emittance at the start of the quadrupole to the sigma squared at the screen through the transfer matrix. In particular, we for sigma squared, we would just need the first two elements, the C and S elements of the transfer matrix. And when doing a quadrupole scan, these quantities, the alpha, beta, gamma, epsilon, it won't change. It's just what it comes before the quadrupole, so those don't change. What change would be C and S of the transfer matrix and sigma squared of the beam. Okay, so And alpha, the twist parameters alpha, beta, gamma are the values that we want to find. So those are the unknowns. C and S are values that we know, and from that we would calculate from the quadrupole, and sigma squared is what we can measure from the beam image. So the unknowns are these three quantities. So what I'm going to do is to rename this minus alpha epsilon, just to make the equations look a bit easier afterwards. I'm going to call this x, big X. I'm going to call beta, so that would be this whole lot. I'm going to call beta epsilon big Y, and gamma epsilon, I'm going to call that big Z. So my equation now looks like this. Sigma squared is equal to C squared X plus 2CS of Y plus S squared. So the idea is that when I do a quad scan, I will for each quadrupole strength, I would have a different set of values of C, S, and the resulting sigma squared. So right now, so let's say I have my for the given for the actual twist parameters in front of the quadrupole. Let's say I apply a particular quadrupole strength, and this gives a particular C, which is called Ci. Okay, and that gives a particular sigma squared, which I call sigma I squared. So this is for the I, the number I quad strength. All right, but the sigma I squared that I would calculate from the equation, it need not be the actual sigma squared measured at the screen, because of various reasons, experimental errors, uncertainties, and so on. So the actual measured sigma squared, I shall call it the actual, the measured for the measured sigma squared, I'll call it sigma E squared with the subscript I for the corresponding quadrupole strength number I. Okay, so this is the measured sigma squared. Okay, and from this, let me just write that out here. This is the calculated one. Calculated sigma I squared, that's the measured sigma I E squared, and Ci as I can be calculated, and X, Y, Z are the unknowns that we want to find. So what we want to do now is this. We want to find the values of X, Y, and Z in order to minimize the difference between this sigma I squared and the measured sigma E I squared. So we make up a function, a target function for minimizing, and that could look like this. We could take the sigma I squared, the calculated one, minus the measured sigma squared beam, and we divide by sigma EI, the measured sigma squared of the beam again. Okay, so that's for one particular quartz strength, and that gives us the if you like, the percentage of fractional difference, and we would add up. Let's see. We would add up the whole lot. Before that, we want to square it. Okay, to give a positive value for each difference, and then we sum it. We sum over all the quartz strength. Okay. And I shall call this target function. Okay, as is not a good idea. Already used that. I'll call it f. Right, that's my target function, f. So this is what we want to minimize. We want to minimize this. Okay. So let me write this in a slightly in terms of the above parameters. So I'm going to just take this sigma I squared expression in terms of CS and XYZ and substitute that into here. So let me do that now. So I'll get F is equal to, right, the sigma I squared looks like this. Ci squared x, okay, plus 2Ci Si y plus Si squared z. So that's coming from up there. Okay. Minus from here E sigma EI squared. So this will be over say sigma EI squared from there, and I'll just put the brackets around it. And then sum over all quadrupole strength. So then next, I'm going to simplify. I'll try to reorganize this a bit. Okay. So Ci squared. So I'm going to separate it out into separate fractions. So that's the first one, plus 2CISI over sigma EI squared y. And for that one, I have Si squared z over sigma EI squared. Sigma EI squared minus the last one will be sigma EI squared over sigma EI squared, which is 1. Okay, so we have this. So this is what it looks like. Now, so this Ci, Si, sigma EI squared, these are all obtained from the measurements. It is the x, y, and z that we want to adjust. These are x, y, and z are the fitting parameters. We want to adjust x, y, and z in order to make f, this sum of the difference, as small as possible. Now to make it look simpler, I'm just going to rename each of these coefficients, this complex looking fraction. I'm going to call this lot here, I'm going to call it A, and I'm going to call this one, I need a subscript I, this changes for different chord strength. I'm going to call that BI, and I'm going to call that one CI, okay, and then I'll just copy over the X, copy over the Y, and copy over the Z, and -1. So that's what it looks like. Now, so when so here's where we are. Well, let's take a look at what we need to do again. Let's think about that. The X, Y, and Z are the parameters that we need to vary, and we want to find the values of X, Y, and Z that will give the smallest f. So that's the chord scan problem. Now there are a number of ways to do this that we know. The first or the more sort of standard way is the thin lens. The thin lens method. Okay, so that will have its own steps. Now, then the other way, which we want to, which we are looking at now, is the thick lens. The thick lens method. Now, for the thick lens method, we are already looking at two different ways. One is using a search method, f-min search, to search for the minimum. Okay. The other way is what I hope to do. I hope to solve this by algebra. Solve by algebra. The question is, can we actually solve this equation? Now, let's go to the equation and look at this again. So basically, the mathematical problem is already given here. It's already specified here, and that is that given the numbers AI, BI, CI, which we obtain from measurements, we want to find the values of X, Y, and Z that will give the smallest f. Now, if you look at this formula, you see that it is actually a quadratic expression, in the sense that when you expand this, because there's a square there, when you expand this, you get terms involving x squared, y squared, and z squared, and also the things like x, xy, and so on. But essentially, it's a quadratic expression. Now, to see whether we can actually solve this by algebra and to see what it means, I'm just going to take a look at an example, okay, to get some idea. So, for example, let's say we want to minimize this expression. Y is equal to y is equal to ax squared plus bx plus c. Let's say I want to minimize this. Now there are different ways to do this, but the way that is relevant to what I'm gonna do is to differentiate it. So I'll do dy dx. Now when I differentiate this, I'll get 2a x plus b. That will be 0. And then I say that at the minimum, this must be equal to 0. And that when this is 0, then I can solve this. And find x is equal to minus b over 2a. Okay, now there are a few things we can understand about this. One thing is that there is only one answer. There is only one answer. Okay, and the other thing is that right, and okay, there's only one answer, and we can ask why there is only one answer from this result. And one way to look at it, without there are other ways like sketching the graph and so on. One way to look at it is to look at this equation, okay, and say that if I solve this equation, I should have only one answer, and it will be relevant to what I do later on to think of this graphically, meaning that if I sketch a graph of this 2ax plus b against x, let's say I get a straight line. Let's say I get a straight line. Then the solution of this equation is where the graph crosses through the x-axis, and that's where I get this minus b over a. Okay, so I can imagine graphically that the graph is a way to show that there is only one answer. So what this tells us is that when we minimize this, okay, we can tell from the nature of the derivative, the dy dx, from the fact that we can only find one answer, that the minimization problem, this minimization problem here, it gives a unique answer. Now then there are other ways to solve this, like we can use f-mean search, for example. But whether or not we find an answer using f-mean search, this problem, right, from this result of the algebra tells us that there's only one answer. Now the other question is, does the answer always exist? All right. Does the answer exist? Actually, it does not. It does not. The answer, well, it does not exist. All right. The answer is no when, no if a is 0. So if a is 0, we have b divided by 0 up there, so it doesn't exist. Okay. But there's something else that we can say. If we can find an answer with this formula, right? If it exists. So this is more of a comment on observation. If exists, then we have only one answer to this problem. Okay. So moving on now to the previous problem. If we now backtrack to here, just clear this. Okay, so I'm going to take the same idea as for the quadratic equation and apply it to here. So in order to solve this minimization problem, I can either do it using a search method like f-mean search in MATLAB, or I'm going to try differentiating it. Now this time there are 3 variables, x, y, and z. So I need to differentiate with respect to each of those and set it to 0. Okay, differentiate this. Need to differentiate with respect to y, and it must be 0. And we need to differentiate it with respect to z, and that must be 0. So if after differentiating, I actually find that there is a formula and there is only just one answer to the problem, and if that exists, then that answer has to be the only answer. So let's have a go. If I differentiate that, let's see what it looks like. I'm just going to put this to one side. So I'm going to try and differentiate this. So I'll start by bringing down the power of 2. So that's a 2, and copy out this lot. So a I x plus b I y plus c I z minus 1, and then I need to differentiate this lot. So I'm differentiating with respect to x only, so those other terms would go to 0. So ai is all I get. So that's ai. Now next, I'm going to rearrange this into a simpler form. So I'm going to collect together the terms, the coefficients of x, y, and z separately. Okay, so I'm going to write, okay, I'll start by separating this out, x, y, z. Okay. And the coefficients for x would be 2ai times ai. So that's the sum of 2ai squared. So that's the coefficient of x. Coefficients of y, that would be 2 bi ai, summed. Okay, so 2 ai bi and summed over I. So that gives me this term, and then after that, for z would be 2 ciai. So 2 ai ci. So summed again over I. Oh, one more term, minus 1 times ai, that's the constant term. So we have ai there, summed over I, and a minus sign. Okay, almost. So to make it look simpler, I'm going to rename this as P1. Okay, P1. I'm going to rename that as Q1. We rename that one as R1, and then that one as T1. Okay, just fill in the X, the Y, and the Z. Minus sign there, and we know that this should be 0. Okay, so write that down here again. This should be 0. Now we can imagine that if I repeat this for this one, derivative d by dy and d by dz, if I repeat those two, I should get a very similar expression, except that the p, q, r, and t would be different. They would have different combinations of a, b, and c. So instead of working through that explicitly, I'm just going to skip through the writing and I'm just going to write out the corresponding forms. So I would expect that that came from df by dz. So I expect that the df by dy would give an expression that looks like this. P, I have a different P, right? So I'll call that P2, a different Q, which I call Q2, different R, which I call R2, and different T, which I call T2. Okay, and then there's the corresponding X, Y, and Z. So likewise, let me get ready the next equation. For the df by dz, that's df by dz, I'll get a corresponding equation again with a different p, which I call p3, a different q3, a different r3, and a different t3. So we end up with these three equations. Now, if you look at these three equations, if you think of the x, y, z space, let's say imagine we have, think of this as axis in this x, y, z space. Then each of these equations, because they're all it's just powers of 1, they're all linear. So each of these is actually the equation for a plane. So what we have here is actually 3 planes, and we know that if you have 3 planes, we can think of the geometrical condition when we can have a unique answer. That's when all 3 planes intersect at a point. Right? When all 3 planes intersect at a point. So, for example, if one plane intersects with another plane like this, let's try to sketch. So let's say one plane there, and this other plane comes here. So 2 planes can intersect at a line. Okay, now if I have another plane, this other plane can cut through these 2 like this, maybe. Okay, and we can end up with and they will intersect at this point down here. So that's one way they can do it, and if that's what happens, then we will get a unique answer. Okay, in this case we'll get one answer only. But they don't have to do this. They can also intersect, all 3 of them can also intersect along a line, or they can be parallel. Okay, so we have these other possibilities, or we can have they all intersect along one line, or they are all parallel. So in either case, we either get lots of answers. Okay, lots. We either get many answers, okay, or we get no answer. Now, and what this means is that the function can't be minimized because there isn't a unique minimum. So The only useful situation is when the experimental data leads to these equations that gives one answer only. Then we have a clear minimum. And that's the case however we solve it, whether we use a search method or use this algebraic method. But what this algebraic method shows is that with this equation, it is now possible to solve the problem. And how do we know whether there is one answer or many answers or no answers? The simplest way is to just apply Gaussian elimination and solve these three equations directly. And if we can get an answer that is the only answer and that minimizes the problem. So using this method, as long as we can use Gaussian, if we can use Gaussian elimination, basically this is just three simultaneous equations with three unknowns. So if Gaussian elimination, if this gives an answer, this gives an answer. So the answer for x, y, and z, okay, and from which we can find the emittance, the twist parameters, and so on. Okay, then this must be the correct answer. Okay, because essentially what we have here is we have a formula. All right, we have obtained here a formula, which is basically the combination of this set of equation and the Gaussian elimination. Right, we have a formula to give us the solution. All right, this must be the unique solution. All right, the unique solution. That's the solution to the quad scan problem. So in much the same way that we can find an answer directly if we solve a 1D quadratic equation.